Well, it's great to see you here in class again. We're getting close to being halfway through week one. Right now you should start to have a feel for what it's like to program in Python. You know about expressions, you know about variables, you know about functions. But really the number of operations that you have at your disposal when building a Python program is fairly limited. So what I'm going to do in this lecture is I'm going to tell you about a few more operations that you have at your disposal to help build more interesting programs. In particular, I'm going to talk about remainders and modular arithmetic. I'll talk a little bit about how to work with strings and numbers, and then I'll finish it off by telling you how to get access to some more built-in functions inside Python. Okay, let's go to it. So let's talk about a few more operations that we can use in Python. For the first part of the lecture, we're going to talk about modular arithmetic. Now, you may not have heard that phrase before, but you actually know how to do modular arithmetic. In third grade, you learned how to do long division. You had a dividend and a divisor, and you divided one into the other. What came out was a quotient and a remainder. So that remainder is actually, essentially, you're computing modular arithmetic when you compute remainders. So I'm going to give you a few examples illustrating how to use modular arithmetic. So let's start off with a really simple problem. Let's say we have a two-digit number and we'd like to compute its tens digit and its ones digit. So how can we get the tens digit? I think it's not too hard. We actually have something that computes the quotient. It's the integer division operator, //. So we could say num integer divided by 10. So 10 goes into 49 4 times. So I'm going to predict we're going to get out the number 4. Sure enough. Now we'd like to also get the ones digit. So how can we do that? Well, we need to compute the remainder whenever we take num. We take the remainder with respect to 10. So let's see if we can find out what the remainder operation is in Python. Let's go to Code Sculptor Python, and we're going to squeeze down here. Let's see, integers and floating point numbers. Let's scroll down. Modular arithmetic, that sounds kind of plausible. And sure enough, that's actually what we're going to use. We're going to use the % operator to compute a remainder here. So we could say %10. Now we could print out the ones digit also, and we get 4 and a 9. And notice we can always reconstruct the original number by just taking 10 times the tens digit plus the ones digit. So there's nothing special about 49 here. That actually works no matter what. All right, let's talk about another example of modular arithmetic using remainder. So this is the classical example that you'll see. It's called clock arithmetic. And the idea is we're going to want to do computations involving hours and either a 12-hour or 24-hour clock. So let's pop over to OneNote here. And what you can see right here is I have kind of two tables. The one on the left here is the 12-hour clock, and so we list all the hours in the day on the 12-hour clock. We have 12 hours that are AM, 12 hours in PM. Notice that the hours start at 12, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If we'd like to do arithmetic on the 12-hour clock, we can almost use remainder to do that. So let's go down here and consider a problem. Right now on this clock, I have it listing the time as listed as 8 p.m. So here it is, 8 p.m. And I would like to skip and figure out kind of 8 hours ahead what the new time would be. So let's go down here and we'll just draw 8 hours, and I'll draw it very carefully. My handwriting's not so great, so I'll try to go slow here. So we go ahead. We end up here, and where do we end up? We end up at 4 a.m. And what do we do up here? We went plus 8 hours. So we could do that using remainder. We could take 8 plus 8, would be 16, and take its remainder 12, that'd be 4. But notice it's a little awkward here because we have to change AM to PM. And the big problem is that in some sense, if we end up with 12 and we take the remainder 12, we get 0. But on this clock, kind of 0 is 12. So the 12-hour clock's not a great clock for kind of doing hour arithmetic. So there's another clock, and it's preferred by the military for this is one of the reasons why. It's called the 24-hour clock. There's no AM and PM. The starting hour is at 0. It's 0000, and it's 0100, 0200, all the way up to 2100, 2200, 2300. And so in this model, we can do clock arithmetic in a much cleaner way. So I have an example over here. I have an example over here that involves, let's see, 2000. What do we want to do? We want to go ahead 8 hours. So let me draw that real quick. So I'm going to go here, and that would be, I guess, 0400. So we'd like to go forward 8 hours here, so we could do that. We could say plus 8 hours. And so what could we do? We could use modular arithmetic to do this, and this actually is much cleaner because we could take 20 plus 8, that's 28, and we take a remainder 24, that's 4. So we can really use modular arithmetic and remainders to actually do essentially computation of hours on the military clock very easily, the 24-hour clock. So let's go back and do that in Code Sculptor real quick. So let's pop back over here. So here we have the hour is 20, so we're at 2000, say it's military time, and we'd like to go through and actually figure out what the time will be after we finish an 8-hour shift. So we could do that. We could say print hour plus shift remainder 24. So if we print that, we got 28 out. What happened here? We thought we were going to get 4. Well, let's think about this as in terms of precedence. Remainder has higher precedence than plus. So what happened here in Python was that we computed shift remainder 24. So let's see, the shift was 8, so it was 8, remainder 24 is 8. We added that to 20, we got 28. So to actually do this computation correctly, what we need to do is we need to go through and add first and then take remainder second. So we do that. What comes out is 4. Okay, let's do another example. Okay, let's look at one more application using modular arithmetic. And this will be something that you'll actually do fairly often in the class. You're going to have a 2D game, objects are going to be moving around, and you have to deal with what happens when an object gets near the edge of the canvas. Maybe it's going to bang off of it, maybe it's going to come to stop, but sometimes you'd like it to actually do maybe something where it wraps around, it goes off one side and comes on the other side. Let me just show you a quick little demo. Here's a part of a game you're going to actually build later on. This is a spaceship, and our spaceship starts flying, and we get close to the edge of the screen, and what's going to happen? Well, it pops on the other side of the screen. It wrapped around. If I go off the top of the screen, I wrapped around. I go back on the bottom of the screen, I appear on the top. So how do we model this mathematically? We could store kind of some information to represent the position of the center of the ship, but when we go off one edge of the screen, we've got to change that position so that it's kind of in a different position way on the other side of the screen. So we can use modular arithmetic to do that. So let's go back and look at this. So let's see we're in a situation that we've keeping track of the horizontal position of the ship. And so the frame that I created was 800 pixels wide. And so we're getting close to that right-hand edge. And we say we need to go right 5 pixels. How could we do that? Well, I claim we can do that using remainders. We could say position is equal to, well, the old position plus whatever the move was. We could do that remainder the width of the screen. And if we print out position, what's going to come out is 2. The position of the ship after we move 5 units right is not over past the right-hand side of the screen. It's actually over on the left-hand screen, side of the screen at position 2. So we've popped from the right-hand side to the left-hand side. The interesting thing, this also works the other way. And to do that, you have to understand how a remainder works on negative numbers. If we take the remainder of something that's negative, what happens is we're always going to get a number back in the range from 0 to width. 0 to the number that we're taking the remainder with respect to. So what's going to happen is when we take the remainder of something that's negative, we're always going to get something that appears on the screen, something in the right range. Let me just do that tangibly. Let's say we were the other way. Let's say we were at position 2. So we're going to kind of reverse this. We were at position 2, and we did a move of -5. We kind of moved to the left. We're on the left-hand side of the screen, and we move left. That's going to be -5. Run the same code. Well, what's going to come out? We're going to get 2 minus 5 is -3. So we have to find -3 remainder 800. And I told you that's always going to be a number between the 0 and the width. So it comes out at 797. So we kind of took -3, we added 800 to it. It gives a number between 0 and 800. It's 797. So we popped to the right-hand side of the screen. So notice using remainders here actually works in both directions. It works when you're moving left, it works when you're moving right, it works when you're going up, it works when you're going down. So remainder is going to be your friend when you're doing screen wrapping.